Hello girls and welcome to this video lesson. Now today's lesson comes from chapter 5 from our GCSE textbooks, but in particular we're going to be looking at the part of this chapter on polygons. Now polygons, literally translated from the original meaning, poly ends up meaning many and gons means angles. Now what this is actually referring to are 2D shapes. So in the olden times they used to think of shapes of having many angles, whereas today we think of them as having many sides, but the principle is exactly the same. There's a lot you've already seen before, so these are the more basic types. Okay, so obviously you've got your triangle there with 3 sides, any quadrilateral that has 4, pentagons of 5, 6, 7 for a heptagon, 8 for an octagon, and we move that down, 9 for a nonagon, and 10 for a decagon. So you really should know these first 10 polygons. Okay, so move on to the next slide. What we're going to try and find out is the angles, first off, in a triangle. So we're going to build this up for any polygon. So we'll use the triangle first off. Okay, now we've seen this before a lot in maths already. You should have seen this in year 7, 8 and 9. If we add up all the angles in a triangle, so fill those in. So if we have A here, B here and C here, if we add those all together, what we end up with, A plus B plus C, we always get 180 degrees, and that's true for every single triangle. Now we've already proved that before in previous years, so we're not going to worry too much about proving it at this point. We're going to take this as a given. We're going to use this fact to help us with some of the other polygons. So we'll move on to a 4-sided polygon, so a quadrilateral. Now the way we use the triangle to help us in this one, what we're going to do is we're going to split this up into triangles, because we can take triangles as a fact, because we've already proved that one. Now I'll take this line and I'm going to split that directly into 2 different triangles. Now if I take the triangles separately, so this one at the top here first, I'll use red. If we call those A, B and C, we already know from the previous page that A, B and C for any triangle will give you 180 degrees. What we've got now though is a second triangle. So we'll use green for this one, and we use D, E and F. And again, if we add those all together, we also get 180 degrees. Now if you look at all 4 angles of the original quadrilateral, you'll see we've got them all covered in one way or another. So what we can do is add our original 180 in the red one to the 180 in the green. What that gives us is the total of the interior angles of a quadrilateral, and it turns out that it's 360 degrees. Worth noting that this will work for any quadrilateral, so you can always split it into 2 different triangles. Right, now we'll move this on to a pentagon, so each time would increase the number of sides. So this one, if we split this one into triangles, use the same process, what it turns out is that we actually get 3 triangles this time, and we use the same principle in order to add up the angles in each of them. So we have the green one at the top here, A, B and C. We have the red in the middle, the D, E and F, and we have a blue one underneath for G, H and I. So you see again we've got all of the angles covered, whether it's divided up into 3s, 2s or just the angle in itself. And what we're going to do is, I won't write it all out this time, but what we'll say is, if we take the greens, they equal 180. If we take all the reds, they also equal 180. If If we take all of the blues, 180 again. So we add those three together. What we end up with is 540 degrees. Now we could go through all of the types of polygon, but all I'll say, I'll just quickly show you the method. If we just split this one up into triangles, we'd end up with 4. Now you should see a pattern forming there, because when we had a triangle, so a triangle has 3 sides, obviously there's one triangle contained within a triangle. A quadrilateral had 4 sides, and we split that into 2 triangles. A pentagon had 5 sides, there's 3 triangles. Hexagon, 6, and 4 triangles. So we're starting to get a pattern forming here. If you can see, if we go from right to left, we're always subtracting 2. So there are always 2 less triangles than there are sides in the original shape. So we can use that to fill in the rest of the table. So the heptagon is going to have 5 triangles, octagon 6, nonagon 7, and decagon 8. Now this leads us to our general rule. So in general, if we have a polygon with n sides, what we have in terms of triangles is n take away 2. Now that becomes very important, because what we're going to use that fact to do is to prove a general rule for finding out the interior angles of any polygon. Because remember, what we did was, before we found the number of triangles, in this case n minus 2 in the general form, and then we know that there are 180 degrees in each of those triangles. So this leads us to this general formula. So a polygon with n sides, the interior angles will add up to n minus 2 times 180 degrees. Right, so we've got a quick example question to go through. So it says here, find the interior angles in a dodecagon. Now this wasn't on our original sheet, but I can let you know that in a dodecagon there are 12 sides. That means we substitute into our formula that n equals 12. So reminding us of the formula, that was n minus 2 times 180 degrees. That gives us 12 minus 2 times 180 degrees. Now 12 minus 2 is obviously 10 times 180 degrees. It's quite a nice simple one. We end up with 1,800 degrees. So in a dodecagon, if you added up every single angle, you would end up with 1,800. Okay, and that's not just for regular dodecagons, that's for irregular ones as well. Any given dodecagon that'll work for. What I'd like you to do now is have a go at this question. Okay, so pause the video if you need a bit more time and work through this one. Right, so in this example, we have a 17-sided polygon. So straight away, we know that n equals 17. All we have to do now is just substitute that into our formula. Okay, so the formula was n minus 2, so that's going to be 17 take away 2. And then we multiplied it by 180 degrees. That gives us 15 times 180 degrees. And when we times that out, we end up with 2,700 degrees. So that is the sum of the interior angles on a 17-sided polygon. Right, we're going to move away from interior angles now and look at exterior angles. Now, exterior angles, okay, so we have, and I'll mark on the interior in blue. The exterior is when we extend the side a bit further. So I'll do that in black. So imagine this is a straight line going across there. The exterior angle is the part inside there, so it finishes off the angle there. So what we have, if we work that round all the way around the shape, so imagine going one way around the shape, we're kind of going this way round. So we have an exterior angle there, work our way down, exterior angle inside there. Next one along, we work across, exterior angle in there, and finally we walk along, across there, exterior angle gets us back to the start. Okay, now one way of thinking of this is imagining you're actually, okay, this is a top-down view of a building. Imagine you're standing here and you're walking around the building. So if you walked around it, okay, imagine the degrees you would turn through. So if you walked all the way around, you would end up getting back to the start again. And the angle you turn each time after you get to the end of each side will be the exterior angle at each one. Now thinking about this logically, if you went fully around the entire shape, what you'd end up with, well, you'd end up facing the direction you started. So if we add up all exterior angles, okay, so that's the sum of those. So the sum of all exterior angles, we end up with 360 degrees. So imagine yourself walking around it, you'd always get back to where you started, pointing in the same direction. So sum of all exterior angles is 360 degrees regardless of the polygon. This is for any polygon, they all add up to 360 degrees. There's a way in which interior and exterior angles are linked. So if I draw on the exterior angle for this one, okay, so imagine that as a continuation of the straight line here. Okay, imagine that going across. We have the red one here, exterior, blue as interior, and you can see, because of the way we've made the exterior angles, if we add an exterior to its corresponding interior, we always get 180 because of the angles in a straight line principle. So once we found the exterior angles, we can actually use that very quickly in order to find the interior ones as well, or the other way around. Right, so first example question, work out the exterior angle of a regular hexagon. Now, the clue is in the question here, because it's given you that it's a regular hexagon. So every angle will be the same size. That includes the exterior ones as well. Now we know that the sum of the exterior angles must be 360 degrees. We know that that's them in total, and we know, because it's a hexagon, that there must be 6 angles. So what we're going to do is we're going to divide that 360 up into 6 equal parts, and what that gives us is 60 degrees. So now we know that the exterior angle of a regular hexagon will be 60 degrees. So it doesn't take too long to use this formula. Example 2, the size of each exterior angle of a regular polygon is 24 degrees. Find out how many sides it will have. Now this time we're given the exterior angle instead of the number of sides. So we're trying to find n. Now we know that if we divide 360 by the number of sides, we end up with what the exterior side angles are. In this case, we're given those angles are 24 degrees. We need to find n. We're looking for that value there. So what we need to do is rearrange this in order to find it. So we do, firstly, we times both sides by n. That ends up giving us 360 degrees equals n times 24 degrees. Then what we can do to get an n on its own is divide both sides by 24. Divide both sides by 24, so we get 360 over 24 equals n. If we do this calculation, we end up with n equaling 15. So we now know that from the original question, this particular polygon had 15 sides, and we found that out by knowing the size of the exterior angles in this particular polygon. The final example I'd like to go through, okay, is worded slightly differently. Okay, so they're giving you a diagram there. What they're saying is that the exterior angles are 20. Find out the angle QPR. So mark that on first off. So QPR is this red one down here. So it's quite a thin sliver of an angle. Now the way we're going to work this one is firstly by using, okay, it's given in the question, or given in the diagram at least, that this is a regular polygon. That means all of the sides are the same length, and that means, with regards to the triangle, that we have an isosceles triangle. Now the key thing with isosceles triangles is it always has two sides the same length, but it also has two angles the same. So that means QPR is also the same as QRP, which is over the other side, filled in red there. So all we need to do is find the angle at Q, and then we can divide, when we take away from 180, we can divide the result by 2. Now how do we find the angle at QPR? Well, we're given the exterior angle is 20 degrees. Now if we were to draw that on, an exterior angle, remember, carries on there in a straight line, and 20 degrees there. So the interior angle at Q, shaded in blue there, is going to be 180 take away the 20 degrees. So it's got an interior angle of 160 degrees. So if that's 160 degrees, to find out what the red bits are, we need to take 180, we need to take off the 160, and then we divide the result by 2, because both those angles are the same. If we carry that calculation, we end up with 10 degrees. So QPR, that angle there, is going to equal 10 degrees. So we use a mixture of the knowledge we have and the fact that this gives us an isosceles triangle in order to help us out. Right, so that's most of the knowledge you'll need for this particular chapter. I just want to leave you with one more thing to think about. Okay, now this is to do with circles. Now circles don't come into polygons because they're thought of not having any angles. Okay, circles only have one side. But if you look at the pattern, just have a look at this. Okay, so we've got the three-sided shape here, 4 and 5 there, so quadrilateral pentagon. Now I've jumped a few up here, but if you can see there, as the number of sides increases, you can see there we start to get a more and more circular shape. So we've got to ask ourselves the question, is a circle a one-sided shape, or is it actually a shape that has an infinite amount of angles? I'll let you decide.